So let's move on. So today we study post-stratification. Before we do, we like to start first domain estimation. So estimation for domains, like you have an original population, but you may be interested in certain gender, right? I mean, male, female, or age group, like 20s and 30s, and sorry, I somehow the internet connection is very unstable today. So I think it's probably better for you guys to come to class rather than uh, attending on Zoom. It's not really my responsibility. So anyway, let me continue. Okay. So domains, right? So we wanna usually a subpopulation. So usually we wanna make inference about subpopulations as well as the whole population. If we plan, so subpopulation, if we plan the subpopulation in advance, then we stratify. We use stratified sample, right? But suppose that information is not available. For example, if I know who is male, who is female in the list, then I can stratify, right? But suppose I don't have that information. I just have a student ID. That's it, right? Then I don't have that information, but I can use that information later because I know, for example, at Iowa State, right? Iowa State, suppose we have a say that we have a 60% male and 40% female, something like that. And I want to do some survey, right? And but I don't have that information, who is male or female in the list. So suppose my list does not show the information, then I can just do some random selection and then check. Then the sample in the sample level, I may have a 50%, 50%. But I know that this is the true population proportion. Then how can I utilize that information? So something like that. So anyway, we'll worry about this. So this is kind of a post-stratification idea. But let's first talk about domain estimation. So if we don't control the sample size for the domain, then the sample size for domain is random variable. So then we need to consider the randomness in the inference. So that is the basic idea. So here's some notation. So UD is a subset of U, and then ND is a size of UD, and the PD is a proportion of elements in UD. And open N is known, but ND is unknown. And YD is a population total of Y in domain D. And Y body is a domain mean of Y in domain D. And then let's use domain indicator function. So let's use Z to denote the domain indicator. So Z K equal to 1 if K belongs to domain, and K equal to Z is 0 if it's not, right? So in the context of sampling, Z is not random variable because in the population, right? In the final population is fixed. So every element in the final population, we have a characteristic, right? The characteristic is just C, K, D, and Y, K, something like that. So they are fixed. We just don't observe all of them, right? So that is the basic setup. So then this is not really a random variable. while the indicator function, right, ik is a random variable. Ik equal to 1 if it's a sample, right? K is in the sample, and otherwise, this is random. Random in the sense that if you repeat your sampling, right? If you use repeat sample selection, then you will have different values of ik. So this is basically just the population. So there's no randomness here, right? It's just the population characteristic. So we are not really discussing anything about expectation or something like variance. No, it's just algebraic notation. So so indicator, because z is an indicator, summation over z, the summation over k of z is just the size, population size for that domain, right? So which is ND. And then z body, which we write it this way, it's just the population mean of zi, zk, and z is either 1 or 0, and it takes 1 if it's a particular domain and 0 otherwise. So it's just the proportion. The population proportion, right? I mean, finite population version of this probability. And then this is just a notation. So we compute S square in the population level, which is this one. And then you can realize that Ci is either 1 or 0. So this one is actually equal to CKD, right? I mean, because it's a 0 and 1, if you square it, it's same. So square it or just the Ci, no difference, right? And then basically this is n times PD. And this one is n times PD square. So then if you n times PD minus n times PD square and divided by capital N minus 1, it will be something like this. So this is essentially just the algebra. Now we have an estimation, right? So now we have a sample and talking about estimation. So the indicator, so this is a sample selection indicator. So that is a random variable. But this is just the Horowitz Thompson estimation, right? Nothing else. I mean, you have a characteristic. So this, in this case, the characteristic of your that you are interested in is just a z. So then we just compute the Horowitz Thompson estimate. The same here. So okay, so that is the basically the n is Horowitz Thompson estimate of ND. So this is population size UD, right? And then on the simple sampling, this one is small n divided by n. So you get you have this notation. And then variance. So variance is variance of this Horowitz Thompson estimator, right? Variance of this Horowitz Thompson estimator have this form. N squared capital S, right? Because it's simpler than sampling. So we apply the variance formula for simple sampling. And then this guy is in the previous slide, right? So we use the formula, which is 1 over n and n p 1 minus p. So we use that, and then plug it here, and then enumerate, then you end up getting this formula. Okay, variance. So same story. We didn't really introduce here. What is this? Small s 3d square is a basically sample version, right? Sample version of c kd minus c bar d square. So this is a population version, right? This is a sample version. And then using the same argument, this will be written as a n over n minus one, p small pd or p hat d minus p hat d. So the if you compare this, right? If you if you remember how we derive this, right? How we derive this, just the same story here. This guy is a sample version, so you should be able to get this. Okay. So and now this is total, right? And now so this is also total, but this total of the indicators. But here this is a total of the y times total of yk times zkd. So y times z is a single characteristic subsets. So basically this is another y, right? This is just another y, different y, say y2k, something like that. So basically you once you write this domain total as just the summation of the another y, then you can apply a Hurwitz-Thompson estimator, which is this one. And then now what we are really interested in could be the domain mean. So this is a population. This is a parameter, right? So this is a population mean in domain, mean of y in domain D. So that is what you are. So that is your interest in. So and then this interesting part of this parameter is that this parameter is a function of another two parameters, right? So this is basically a function of two unknown parameters. These two parameters are unknown. So that means your estimator of this guy should be this one, right? So that is actually this. So we just mimic this functional form and plug in the estimators. Then you can see that this is a nonlinear function. It's a nonlinear function. So that means the inference may be somewhat complicated. So usually we don't know how to compute the variance for nonlinear function of random variables. But we can, if we can linearize it, right? So suppose I can basically here D and hat D. If I can linearize, say C1, C0 plus C1 Y hat D, right? So, so the equality here cannot be true, right? It's not true because the left side is nonlinear and right side is linear. So how can that be the same, right? That's not true in general. But hopefully that is a Newton's idea, right? I mean, suppose what is the best approximation, right? What is the best approximation? So once you get best approximation, and some theory says that the remainder term can be ignored, and you can probably apply the formula for linear estimator. And for the linear estimator, we know how to compute the variance. So that is basically the idea. So you can, so the formula is, so that is basically the Taylor expansion, right? So the Taylor expansion is really important technique. So we repeat this technique a lot of time, but let's do it one by one. So once you write this way, right? Once you write this way, we should enumerate with respect to its expectation. So we have a two random variable here, and two random variables will be enumerated. Taylor expansion will be used around its expectation, and the expectation is, so the expectation of this guy is this guy will converge to ND, and this guy will converge to YD. So we our enumeration should be with around the mean, right? Around this system. So then this is the first term, and then linear term we write it so. But this is the first derivative with respect to the first component, and this derivative with respect to the second component, right? And then what you need to do is to actually write down exactly what it is, right? So because f is, so f x1 x2 is what here in this case is x2 divided by x1. So that means this guy, so you are expanding it with respect to the second component. So then that means this is 1 over 1 over x1, uh, which is n1. So that is this. Same way here, this guy is a derivative with respect to the first component, right? Then means that is x2 divided by x1 square, which is actually minus y d divided by n d square. That is this one. So that's how you get this linearization. So this is indeed a linear of two random variables, n hat d and y hat d. This is indeed a linear function of the two random variables. Yeah. Hmm? The partial derivative, it's only the first one.
Yes, I thought this is the second order.
Oh, no, first, you think too much. So, yeah, when you really investigate the bias, order of bias, then you need a second order extension. But when you talk about variance, first order is enough. Okay. So, so then once you do that, then you can actually write it as a kind of y bar d plus 1 over n, right? And y hat t minus y n t square n hat d plus you have a kind of constant and y bar d plus y bar d. So this they cancelled. So basically this guy and this guy cancels to each other. So that you don't have to, so right, if this is so nd divided by yd divided by nd, this guy is yd divided by nd squared times nd. So they are actually the same. So they, and end of the day, we get some nice cancellation. Okay. So then we have this only, so we have only to worry about this part, which is okay. Now on the so this one is for general. So this is approximation of the ratio. So this is sometimes they put, but this is so common and popular. It has a name. That's basically ratio, right? You have a ratio of two random variable. So ratio estimator, sometimes it's a ratio. But it's not, ratio estimator is a separate thing. So we just call it ratio. So so then now let's try to understand this formula further. So y bar d is what? Variance over 1 over nd and y hat t minus y bar t and hat t, right? That is the formula. And then let's write it further. How to write it using the Hurwitz-Thompson estimator. So then this guy, see, this guy is 1 over summation over I equal to a 1 over pi I CID YID YI, right? So CID YI. But this guy is also summation over 1 over pi I CID. So that means you get some common thing here, right? You have some common thing here, and then the only difference is that you have a yi, the other one is y body. I should write it smaller. Let me write it again. Oops. Okay. And then, so this is for general formula. And then now we suppose a simple random sampling. This one is a small n divided by n, right? So you can obtain this one on the simple random sampling. And then what is the form of the variance of Hurwitz-Thompson estimator, right? I mean, on the simple and sampling. So remember, y hat Hurwitz-Thompson on the simple and sampling is nothing but n square over n 1 over n s square. So we're gonna use that, right? We're gonna use that. But here you have a y only, right? But here this is the whole thing is y. So what I'm saying, okay, maybe I will write it. So so this part, so I'm okay. So how do we get this one? So basically variance over n over n I equal to a ci d yi minus y bar d is just nothing but a total of y, say yi star, which this is, so this is yi star, right? So then this guy is n over n square n, 1 over n times 1 over n s square, which is minus n times I just wrote down the formula for s square in more detail. Nothing else, right? And then you recognize that this summation of yi star, summation of I equal to n, is indeed 0. So that because by the definition of y bar d, right? Y bar d is the indeed this guy. So this guy is 0. So so that means you have this one. So that is, and the square and because CID square is just a CID. So get this one. Yeah. So when you just try to follow my derivation, you are actually in the passive mode, right? You just try to understand what I show. That's very difficult actually. Rather you may try to be more active, proactive, right? You try to show it first. For example, I mean, if you use the lecture note and you try to show, and then maybe it's not easy. Maybe there's some step you didn't catch, right? And then if you see this now, once you try it first, and then if you see this one, then you know where you will immediately realize where you had the trouble. width, right? So that's actually more efficient way of learning. So actually spending some some investment, some initial time investment help you a lot actually, and overall you save your time. So anyway, that's just my tip. And then now this guy, it's just algebra, I guess, right? So you can you know you can separate out. So the first component and the second component. And the second component, actually, you have a cancellation, right? N square cancellation. So, and then the only thing left with is this ND square, which is this one. The first part is, this guy, right? And then you have a cancellation and capital N cancel. So then ND on the simple random sampling, ND is N times the proportion. So this one. So at end of the day, you will get this formula. So one interpretation of this formula is that you can kind of start with the simple random sampling from the subpopulation, right? So this is a kind of a variance formula from the subpopulation UD, okay, over sample size. So basically this is your original population, but this is your subpopulation, right? And then if you do random sampling, simple random sampling, you're essentially kind of selecting this. So that is actually you can view it as uh selecting this sample size from this population. So now we're gonna move on to post-stratification. So post-stratification is that the group information is not available at the time of sampling, but that is but you know the group information after the sampling, okay? But you also, but on the other hand, you have this information. Population size is known. So let me use the example again. Male, female, right? So population, suppose we have a 60-40. Sample, we have a 50-50. By chance, right? So population level, we know they are 60-40. But by randomness, we get this proportion in the sample. Then that means what? That means, okay, from the sample, I have a 50-50 male, female. But I know that males are more, right? We have more males than females in the population. So that means somehow we have a more selection, right? Oversample. We oversampled the males by chance. And we undersampled the female by chance. So then to reflect the information, right? To reflect the information in the population, it makes sense to downweight males and increase the weight. What is the opposite way of downweight? English. Overweight? Maybe overweight, right? Overweight. So downweight the male and inflate the weight for females, right? So that is the basically key idea here. So this formula is actually doing that business. Okay. So if Y, for example, if Y happen to be indicator of the group indicator, then you get exactly this, the information, same information, because Y hat G and hat G will be cancelled if Y happen to be the same as a group indicator. Okay. Now from here we need to derive this asymptotic variance. So again, this is a ratio, right? This is a ratio. So this is basically nonlinear. So we need to do Taylor expansion. Okay. So and then we know that Y hat G is equal to YG, and hat G equal to NG. So then we use Taylor expansion to get. So remember, we already did computed this already, right? For particular G, we already did that. So what is this? Right? So that is what we derived in the previous slide here, right? Page 7. So we derived this already. So we just plug in. So no head. Oops. Okay. And then this one is indeed Y plus yeah. So G 1 over pi I minus yi minus y bar. So then that actually shows, right? So that is post is approximately equal to y plus right? So that is result of the Taylor expansion. Mm. So which is not this one, which proves the two. Okay, so now let's try to. So this is for the general sampling design, right? And now let's try to understand this formula further using simple random sampling, right? So let's use a simple random sampling, then try to understand what it is. So basically, we know this formula is but this is actually just a, so the idea is you can just write it. Okay, maybe, yeah, you can write it as a G equal to 1 to G, same thing. Okay, let me, sorry, let me back up. So let's write it, this guy, and yi star, where yi star is indeed G equal to 1 to G, right? And then yi minus y bar G times Cig. So Z, so what is this guy? So Cig equal to 1, 0 if I call UG, otherwise. You can use the indicator function, right? To define the where it belongs to, right? The y. And then once you do that, then once you use this yi star notation, then this is just a formula for simple sampling is easy, right? So you have the formula should be, oops, formula should be, oops, anyway, yi star square plus n times y bar star square, something like that. This is nothing but the variance formula for simple random sampling. And now, what we are going to do, check is that this guy is equal to 0. So if you take the summation over all I, this will be 0, right? Because we are subtracting the yi by group mean. So end of the day, it will cancel out to 0. So then this guy will be 0, so you don't have to worry about this one. And this guy is indeed can be written as. So so what is the basically what is the I equal to n yi star square. Well, you can use the use this indicator, right? So I go to n g square cig. You don't have to worry about the cross product term because they are mutually independent. I mean, if just the group partition is you know is exhaustive and exclusive, right? So that is basically this guy. Same thing. Okay. By the way, this one formula is indeed the same as the variance formula on the stratified sampling with the proportional location. Remember, let's recall, what is the variance of the y-hat stratified sampling, right? On the proportional location. That is actually this guy. Within, right? So remember, simple random sampling. What is the variance of a simple random sampling? That is SST, right? Sum of square total. So that is a simple random sampling. We have just a factor, usual factor times SST, where SST is, right? This is SST. What is SS with? SSW. SSW is within. So it should be right in the group within straight. Okay. Now, so these two sections are in the context of survey sampling. But we also have the same very similar concept in the experiment. So this is causal inference topic. In particular, we are talking about experiment, randomized experiment. I should say randomized. Okay. So we're going to move on to in the context of randomized experiment. So recall the last week, I think it's last week, right? Last week we covered stratified randomized experiment. So stratified randomized experiment using the male female twin example, right? So we want to balance, but suppose you don't know that we don't have that categorical. So here the categorical covariate means, for example, male, female, right? So that is, if that information is available, it makes sense to use that information and achieve some covariate balance. So that the presumption is that covariate information should be available in the final. Now, suppose that the individual covariate information is not available in the final population, but its summary information is available, then we may use post-stratification. So somehow we don't know who is which one is which, but still we know the marginal distribution. So that is if so. Here's a kind of notation. Yeah, we slightly use a different notation in, but so yeah. So previously I used CIG, right? In the sampling package, but in the design I used X. So in the experiment, but it's meaning the same concept. And that's so this is known, WH is known, even though we do not know xi at the time of sample selection. And the sample is selected by a completely randomized experiment. So then, finite population parameter. So we are interested in average treatment effect. And then this is basically what? yi1 minus yi0, right? And this guy is what? 1 over nh. You could, yeah, we use the UH notation. So then this one is I equal to UH yi1 minus yi0. Okay. So that is basically straight mean of towers in the population level. And then this is known. So we know this WH, but we do not know tau H. Right? So we want to so we leave WH alone, right? We know that, so we don't have to worry about it. But we want to we never really observe this tau H because of the potential outcome framework. We cannot really it's fundamental missing data problem. So we use randomization, right? Completely randomized experiment, and then we can compute this. So this is actually a time, right? Within stratum H. Same story. The only tricky part is that the denominator. So in stratified sampling, they are fixed. But in the post-stratification, in the completely randomized experiment, they are random variable. On the completely randomized experiment, right? On the completely randomized experiment, we are not really controlled. We do not fix the sample size, right? The treatment group and control group. We don't do that because we don't know which one is which, right? We don't know who is male, we don't know who is female. So we cannot really do the specification. So then we just use it. We can still use the same formula, but so first of all, sometimes this denominator is 0. Could be 0, right? Because of the randomness, they may not be available, right? You may end up getting no sample in female, right? For example, it's possible. So then we may not be able to compute the post-stratification estimator in that sample. So, but at least so I think to be more rigorous, maybe this is only so only the NH1 and H0 are all positive. So that we need that condition. In stratified sampling, in the stratified randomized experiment, we don't have to worry about it because we fix the sample size. Okay, so here's a talk example. So the design, right? The design is set the same. I mean, we use completely randomized design. So completely randomized experiment design. But from the completely randomized experiment design, we can still compute two types of estimators. One is the original time estimator, which is basically you compute the mean of treatment group. So this one, mean is what? 5. Right? Mean of the 4, 6, 5 is 5. 3, 4, 5 is 4. So you get 5 minus 4. Then that is 1, right? So this is the tau hat on the CRE. What is more tricky is this guy. So how to compute this? Well, this guy, we need to use this formula. So so that means, okay, let's first consider what's the proportion of a female. So we have 3 females. So basically the proportion of female is half. And then we want a treatment within the female group, right? Within the female group, we compute the mean difference. So which is 5 minus 3 plus male. Same story, right? In the male group, we have a 5 minus 4.5. Another way is you just compute this and half 5, which is 5, and then half is 3 and half 4.5. We get okay. So we just use this formula, right? We just use this formula and computed post-stratification estimator. So now the next question is, okay. So the point estimator has the same form as the stratified estimator, right? So in terms of point estimation, there's no difference between the stratified estimator and post-stratified estimator in terms of the point estimation. However, variance, there's a tricky part because variance, in terms of variance, we again, denominator is random. Denominator is random, so that involves some additional algebra, which is basically Taylor expansion. So tau hat post-stratified estimator is a summation of h equal to 1 to h wh tau hat h, right? And so this guy can be written as this way. So this is t. Treatment is equal to small t. So it could be 1 or 0. Right? So the randomness comes. So again, this is a random variable. So we need to do Taylor expansion. We need to apply Taylor expansion to investigate the property or symptomatic property of this estimator. But this is also the same ratio, right? Same ratio. So the ratio, we already apply the Taylor expansion to the ratio before, so we should be able to apply, obtain the similar, apply the same technique to get some linearization. So So now, before we apply, we should investigate what is the expectation of the numerator and denominator, right? So each component in the numerator and denominator. So what is the expectation of this guy? What is the expectation of this guy? Okay. So then when you try to compute the expectation, you need to first think about what is the random variable, what is not random variable, right? So the random variable here is Ti, capital Ti. So and this is essentially completely randomized, essentially simple random sampling. So supposed to be straightforward. So basically, we have N1, right? So we have N1 and N0 fixed. We know how many sample we're gonna, how many treatment group we're gonna select, how many control group we're gonna select. We know that, right? We fix it in advance, and then do random selection. So then this T. So actually, this guy, I guess, this guy is the expectation of. So expectation of this guy is NT by N. So then everything else, so then the whatever left is this guy. This is summation of y. Same way, you have an expectation of this guy, right? Apply expectation, then the sample, the population size is capital NH. Okay. And so the ratio, right? The ratio, you need to expand around their expectation. So the expectation of this guy is this guy, and then expectation of T hat is this guy, and but you have some cancellation. Okay, so then you get this one. So I would, okay, maybe once you are quite comfortable with deriving the Taylor expansion, maybe it's good time to memorize the formula. Okay, so that is actually a frequently encountered formula for ratio. So you should first understand how it comes from, but once you understand it, it's probably better to memorize it. Then you can use it frequently, right? Like multiplication, you memorize, you don't really derive every time, right? I mean, same thing. So then this guy is this guy, this guy is this guy, C hat, D hat, and then this guy is this guy, which is this guy. And then and then now we once you write this way, once you obtain this part, and then next step is to recall the definition of what is a C hat and what is D hat, right? And then write it again. So C hat and D hat is defined here. So you just bring back its definition, and then end of the day you can write this. So the only thing random is here. So that means it is indeed linearized because it's a function, linear functional, right, of random variable. Okay. So that means, oh, I should have. So this is actually should comes in here, but we already covered the linearization several times. So hopefully that's okay. Okay. So then what is okay? Now maybe I should okay, right. So let's actually we have something to show. So this is h equal to 1 to h w h tau at h, which is mu hat 1 minus mu hat 0. And then now using the Taylor expansion, you get this one. So y bar 1 minus y bar 0 plus this one. And then and okay. So actually plus minus minus 1 over oops. So the first part is essentially finite population uh, uh, average treatment impact. And then we have a cancellation. And then what is left with is essentially the N1, right? N1, and then summation of H equal to 1 to UH. We can call it TI times. So we use EI1, we use EI0, then this EI1 plus 1 minus TI EI0. Sorry, should uh, so no plus, actually minus. What's going on? Maybe I should write it. Okay. 1 over N1 I EI1 minus 1 over N0 H equal to 1 to H 1 minus TI EI0. So that gives this formula. Well, I think this is probably a good place to, and then this one, once you have this one, then we use the so this is a completely randomized experiment formula, then you can get this result. The main difference is that instead of yi is changed to ei. So remember, in the completely randomized experiment, we should have a yi1 and yi0, right? Which is actually ti is just yi. But in the post-stratification, we actually have a residue. So usually the residual using the regression of y on the indicators, group indicators, stratum indicators. Yeah, I will explain a little bit further in the next class. So that's all for today. Thank you.